For over 400 years, every map of the cosmos we've ever drawn relied on a single tool: light. From Galileo's first blurry sketches to the staggering high-resolution vistas captured by the Hubble Space Telescope, if an object didn't glow, reflect, or emit electromagnetic radiation, we couldn't see it. That reliance creates a massive blind spot when it comes to black holes. These objects pack so much mass into such a microscopic point in space that their gravitational pull becomes inescapable. They literally swallow the very light we need to detect them. And when two of these dark titans collide, the resulting merger is nearly incomprehensible. A single collision releases 50 times more energy than all the stars in the observable universe radiating at once. But despite being the most violent, explosive events to happen since the Big Bang, they don't give off a single spark. To our most advanced optical telescopes, the site of this cosmic cataclysm looks like completely empty space. As long as we depend exclusively on catching light, we remain blind to the universe's most extreme and consequential phenomena. Albert Einstein predicted how to find these invisible giants as early as 1916, tucked away in the mathematics of his general theory of relativity. Einstein proposed that gravity isn't just a magnetic pull between objects. Instead, space and time form a physical, flexible fabric. Drop a massive star or a black hole onto that fabric, and it bends downward, much like dropping a heavy bowling ball onto a trampoline. When two black holes get caught in each other's orbit, they violently churn that fabric. Their inward spiral whips up ripples, gravitational waves, radiating outward in all directions at the speed of light. Unlike light, which gets easily blocked, scattered, or absorbed by interstellar dust and gas, gravitational waves are distortions of space itself. They pass right through stars, planets, and nebulas as if they aren't even there. Because absolutely nothing can block or degrade these ripples, they carry the pure, pristine story of their violent origins directly across the cosmos to our front door. There's a catch, though. By the time a ripple from 1 billion light-years away finally reaches Earth, it has flattened out. It will stretch and squeeze our local space by less than 1,000th the width of a single proton. Measuring something that microscopic requires an absurd feat of engineering. The Laser Interferometer Gravitational Wave Observatory, or LIGO, built massive 4-kilometer-long concrete vacuum tubes stretching across the American landscape to do exactly that. This diagram shows how the L-shaped detector works. A central laser is split down those two perpendicular 4-kilometer arms. When a gravitational wave passes through the Earth, it subtly squeezes one arm while simultaneously stretching the other, knocking the two lasers out of sync, just enough for the sensors to catch the shift. And this search goes far beyond a single facility. Scientists in India, as part of the Indian Pulsar Timing Array, utilize giant radio telescopes to track the incredibly precise ticking of distant, spinning stars. By measuring microscopic delays in those stellar metronomes, they can catch the slow, low-frequency gravitational waves that Earthbound lasers miss. Over decades, we managed to link kilometers of empty desert and global radio arrays into a single, planet-sized ear, all tuned to catch a whisper from the deep dark. On September 14, 2015, that ear twitched. The LIGO detectors registered a tiny, precise chirp, a signal named GW150914, originating from two black holes that collided over 1 billion years ago. This measurement turned space into a physical medium we could record, capturing a 1 billion-year-old collision as a tangible pulse. Following that chirp, astronomers detected the collision of two neutron stars, proving that these impacts act as cosmic forges to create the universe's supply of gold and platinum. The ultimate goal is to look even further. By refining how we listen to these ripples, scientists hope to eventually detect the primordial background waves left over from the Big Bang itself, an echo from the exact moment space and time were born. Gravitational waves have moved astronomy out of the era of silent movies and into the age of talkies. The invisible universe has been speaking to us all along. We finally learned how to listen.